Hey GED students and math students all over. I know I've been harping on how divisibility is so important. It really is. Divisibility is the key to unlocking all these skills you guys struggle with, like long division, like fractions, reducing them, adding and subtracting them, like factoring. Things that students really struggle with as a general rule are often explained or made much simpler by the concept of divisibility. So we've been talking about the divisibility or tricks or rules, and the only thing I mean by that is that I notice patterns to times tables, and we can use those patterns to know when a number is divisible by another number, when it divides perfectly with no remainder. So today I want to talk about a certain brand of divisibility tricks known as the sum of digits tricks. Now, as it turns out, more than one number has a sum of digits trick, but we're going to start with the very first sum of digits trick, and that's the 3 times tables. So in order to see what I mean, I'm going to list out my 3 times tables. So I'm just counting by 3 here. 3, 6, 9, 12, 15. Now some of my students struggle to count by 3's. If that's you, don't feel bad. All you're going to do is hold up 3 fingers for me, and you're going to just count 3 more each time. So 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, and so on and so forth. And I want to take it up a little bit so I can make a point to you. So 43, 44, 45, 46, 47, 48. I think we've gone far enough. Okay, what I want to do is establish a nice pattern here. Now, people actually lie to me about the patterns on the 3 times tables at all. All the time, you guys tell me lies, mostly because you make false assumptions. The first assumption that people tell me all the time is, Kate, I know. They tell me, I know, light bulb goes off in their heads. They tell me 3 is an odd number, and so every number on the 3 times tables is odd. They tell me if it's an odd number, it will divide by 3. And I'm like, no, I don't think so, y'all. Let's take a look at this list. I mean, look at the first number. Yeah, 3 is odd, but then 6 is even. 9 is odd. 12 is even. Yeah, you did not notice a pattern. I'm not quite sure what you thought you were looking at, but the 3 times tables are not odd. Not true. That's a lie. Okay, next thing that students tell me, again, it's because they assume that they're going to see an end of, they assume they're going to see a final digit divisibility trick. They tell me what they think it ends with. They tell me all the numbers on the 3 times tables end in 3, 6, or 9, Kate. And they think, oh, brilliant idea. I finally caught on. All the numbers end in 3, 6, or 9. And I'm like, is that true? Let's take a look. Well, I start off with 3, 6, 9, and some of them do end in 3, 6, 9, but obviously not all of my numbers on the 3 times tables end in 3, 6, and 9. Look, there's a 2, a 5, an 8, a 1, a 4, a 7, a 0. I can end with anything and still be on the 3 times tables. So obviously this thing you guys think you notice is also a lie. So what really is the pattern of the 3 times tables? Reason why you guys are struggling with it so much is because you're just used to looking at the final digit, the butt of a number, to look for divisibility. As it turns out, not all divisibility tricks are final digit tricks. There's also what we call sum of digits tricks. And what is a sum? We learned that way back early in our math career. A sum is the answer when you add. And what is a digit? Those digits are those individual number symbols that we use to build up our number system. Like, for example, 217 is a 3-digit number. It's one number, 217, but it contains 3 digits, the digit 2, the digit 1, and the digit 7. Okay, so if I say sum of digits, I'm simply asking you to add the individual number symbols that you see within the number. So let's check it out and see what happens. I erased my T by accident. Okay, here we go. So for the number 3, that's just 1 digit, so there's nothing to add. Same thing with 6 and same thing with 9. But starting at 12, I want you to see what would happen if you added 1 and 2. 1 plus 2 is, of course, 3. How about if we added 1 plus 5? We'd get 6. 1 plus 8, we'd get 9. Are you beginning to see a pattern emerge? What if we did 2 plus 1, 3? Or 2 plus 4, again 6. 2 plus 7 would again give us 9. Same thing with 3 plus 0. Oh, I just wrote 0 and it's not 0, y'all. You better watch me. 3 and 3 plus 3 would give us 6. And 3 plus 6 would give us 9. And right here is when students start getting real excited. They're like, 369, 369, 369. Everything on the 3 times tables adds to 369. Not exactly. Kind of. Let's keep going. Look at the next one. 3 plus 9. Well, 3 plus 9 doesn't add to 3, 6, or 9. It's too big, but 3 plus 9 does add to 12. Now, 2 things I'd like to point out about 12. First of all, 12 is on the 3 times tables. 3, 6, 9, 12. So 12 is divisible by 3. 12 is divisible by 3. That is, in fact, the sum of digits rule. If the sum of digits is divisible by 3, it divides perfectly with no remainder. Then the original number is divisible by 3. 3, 6, 9, 12, all these numbers I'm getting, all these sums of digits I'm getting are on the 3 times tables, meaning they're all divisible by 3. Okay, so 42, same thing. You're going to see 4 plus 2, you get 6, a number that's divisible by 3. 4 plus 5, you get 9, a number that's divisible by 3. 4 plus 8, again, you get 12, but that is a number divisible by 3. Now, let's say you don't know your 3 times tables very high. You're like, Kate, 3, 6, 9 is as far as I know. After that, I get a little confused. I'm going to need to use this sum of digits trick a lot. Well, then I'd like to point out to you that these 2 numbers here that we got that weren't 3, 6, and 9 are still 2 digits long. Let me say that again. They're still 2 digits long. So if you wanted to, you could keep adding the digits that you got until you get to a 1-digit number. So this is 12. It's still 2 digit long, so I could add 1 plus 2, and I would indeed finally get to 3. Same thing here, 1 plus 2, and I would eventually get to 3. And so I can see that, yes, if you keep summing the digits until you reach a 1-digit number, then anything on the 3 times tables will sum to 3, 6, and 9. Or another way to think about it, and this is the mathematical way that you should walk out of here with, if the sum of digits is divisible by 3, then the number is divisible by 3. Let's look at some fantastic and fabulous implications of this that you have to know for your GED test. Okay, first of all, this skill could come up just like this. In the first 5 problems of the GED, you will have divisibility problems. So someone could just straight up ask you, is 3 a factor of, and they could give you a giant number like 675. So is 3 a factor of 675? Hopefully you guys know that when I ask if something's a factor, I'm asking if 675 is divisible by 3. 3 is called the factor if 675 is divisible by 3. So I'm asking if 3 divides into 675 perfectly. Or another way of thinking of it, I'm asking if 675 is on the 3 times tables. Okay. So could you do long division to figure this out? Of course you can. Long division always works. Or you can use that lovely divisibility trick. You can say, oh, look, I'm looking for 3's. That's a sum of digits trick. Let me go sum the digits of this possible number over here, of this possibility. So I'm going to add the 6, the 7, and the 5. Now 6 plus 7 is 13, 14, 15, 16, 17, 18. I get the number 18. And all I have to ask myself is this number on the 3 times tables? Why, yes, it is. 18 is on the 3 times tables. Or again, if you don't know your 3 times tables up that high, You could continue to keep adding. Add that 1 plus 8, you'd get 9. And of course, you could see 9 is on the 3 times tables. So is 3 a factor of 675? Why, of course it is. On the other hand, they could flip the language again. They could ask you something like, is 2042 a multiple of 3? Again, whether they talk about the factor or they talk about the multiple, it's all divisibility. Factors are the numbers that multiply. Multiples are the numbers you multiply to make the larger numbers, if you think of it, when you're talking divisibility. So same exact question. Is 2042 a multiple of 3? I'm asking, can I divide it perfectly by 3 and get no remainder? Or is it on the 3 times tables? Okay, so that being said, I could check this by division, or I could use my lovely divisibility trick, which is a sum of digits trick. I don't like long division, do you? So I'll do a sum of digits trick. So is this a multiple of 4? Let's add up the digits real quick. 2 plus 0 is 2, plus 4 is 6, 7, 8, I get 8. Is 8 on the 3 times tables? Of course it's not, and so neither is 2042. Is 2042 a multiple of 3? Absolutely not. Another way this beautiful, glorious, gorgeous skill comes up is in reducing fractions. I'm sorry. I love GED students. They're my people. I spend all my days with them. I'm so proud of them in so many ways. But for the most part, GED students suck at reducing fractions. One of the reasons why is because y'all give up too easily. When you look at a fraction like 42 over 51, no obvious common factors come to mind. You look at that and you're like, I have no idea what goes into 42 and 51. How could I ever reduce this? And you don't even bother to test these numbers for various divisibilities. Now, I agree with you that these two numbers can't divide by 2 or 5 or any of the obvious ones like 10, the ones that we love. You know, this is an even number, but this guy's odd. Neither one of these divides by 5. Neither one of these divides by 10. You guys give up because it looks hopeless, because there's no easy n-digit divisibility. But a really quick sum of digits could show you that these numbers do both divide by 3. 5 plus 1 is 6. 4 plus 2 is 6. Both those numbers are on the 3 times tables. What I just learned is that 42 and 51 are both divisible by 3. Careful. They're not divisible by 6 necessarily. That's what some students think. No, it's just if I add the digits together and they come to a number on the 3 times tables, then these both are divisible by 3. Meaning that this fraction, even though it might not look like it to you, can be reduced. The top and bottom have a common factor of 3, so I can divide them both by 3. 3 goes into 4 once, remainder 1. 3 goes into 12 14 times. If you're wondering what kind of ninja magic dividing I'm doing, it's called sight division. It's beautiful. I have a full-length video on it. You want to know how to do it. 3 goes into 5 once, remainder 2. 3 goes into 21 7 times. And there now, I know that I'm done reducing this fraction. 17 is a prime number. It's not divisible by anything but 1 or 17. And of course, I couldn't divide 14 by 17. So another way this concept will come up, okay? So great. Sum of digits trick, super useful, and that is the divisibility trick to test for 3's. So anytime you want to answer the question, is it divisible by 3? Which, as it turns up, is a question that comes up so much in math, it's ridiculous. You can go the shortcut way. It's known as a sum of digits. Great. Now, as it turns out, 3 isn't the only number with a sum of digits trick. A few other numbers, any number that contains a 3, think of all the numbers on the 3 times tables, will involve a similar trick. So stay tuned for a couple future videos. Next, we're going to look at sum of digits for 9's, and then we're going to look at the divisibility tricks for 6.